Okay, so this is review session number 2 for the final exam of Math 103. Okay, so just a quick outline of what we're going to cover. So yesterday we already covered the first half of the course, which was all like derivatives, everything to do with that. This time we're going to cover like optimization and mainly all of the area under the curve stuff, like integration, and the end of the course with like probability and Taylor series also. All right. So yeah, to get started, so a big topic was optimization. So there's a strategy for how you want to approach these optimization problems. First, you want to find some actually determine what is being maximized or minimized. Like what is the question asking you? Write an equation so that's the equation that you're going to be taking the derivative of. Then if your equation has two different variables, you want to make sure that your equation just has one variable so that it's single variable calculus and we can take the derivative more easily. Then you want to find the critical points. So that involves taking the derivative, setting it equal to 0. And if necessary, you might need to find a domain so that whatever critical point you have is actually possible to be a critical point. Okay, so I have an example here. So here we have a 216 meter squared rectangular lettuce patch. It's being enclosed by a fence and divided into 2 equal parts by another fence parallel to one of the sides. What dimensions for the outer rectangle will require the smallest total length of fence? So here they're saying that this is some large lettuce patch and they're going to divide it into 2 equal parts, which is this dotted line. So if the fence is all of this outline and the part that we're dividing. So the highlighted part is the fence. And they're saying what dimension of the rectangle will require the least amount of highlighted parts. So how do you do that? What are we trying to minimize? We're trying to minimize the length of our fence. So what is the length of our fence? That's the highlighted part. So I labeled them. We're going to need 4 L's and 3 W's. So our length is 4L plus 3W. That's what we're trying to minimize. Now, what do we know? They gave us that the area is 216 meters squared. So we can say area is going to be length. In this case, our length is 2L times the width, which is W. So right now we know the area is 216, or we can write that as 2L times W equals 216. But remember, our equation right now is 4L plus 3W, but we only want our equation to have one variable. So how do we get rid of the other variable? Well, we can find out maybe what is W. And so that way we can substitute it into our original function so that we only have one variable at the very end. So what is W? W is, if we divide both sides by 2L, we get 216 over 2L, which is 108 over L. Now we can substitute this W in to our L. So which is right here. So we can substitute that in here, and we get that our function now is 4L plus 324 over L. And we're going to call that our function f. But note also in this problem, we're going to have a domain because your length can't be 0. If your length is 0, then it wouldn't make sense. You would just have like a line as your fence. So our domain is going to be from 0 to infinity, not including 0. That way it is more realistic. Okay, so now that we have our function, let's take the derivative. What is the derivative of this? It's 4 minus, this is 324 L negative 1. How do you take the derivative? You bring the exponent down so that it's negative 324, and then you subtract 1 to the exponent. So you have an exponent of negative 2 now. So now we have this. Let's just write it more cohesive. So let's put everything to have the same denominator. So if I multiply this 4 by L squared over L squared, we get 4L squared minus 324 over L squared. This is our derivative. And I just simplified it to 4 times L squared minus 81. Now, how do you find the critical points? You set the derivative equal to 0. In this case, we have a numerator and a denominator. So our critical points, we want to consider when our derivative is 0 and also when does not exist. It equals 0 when this numerator equals 0. So I set the numerator equal to 0. The derivative does not exist when your denominator equals 0. So I set L squared equal to 0. So over here, you get L equals 0, but this is out of our domain because remember, our domain was not including 0. So we don't have to count this as a critical point. We don't care about this one. What about over here? What critical points do we get here? We get L equals 9 and negative 9. But negative 9 is also out of our domain, so we can ignore that. But 9 is in our domain. So right now, our only critical point that we care about is L equals 9. Now, an extra step is that we want to check to make sure, is 9 a minimum? Like, is it going to give us the least amount of fence that we need? Well, let's check. You could either use the first derivative test or the second derivative test, but let's use the second derivative test here. Either works, but I picked second derivative test. How do you do that? You find the second derivative. So what was our first derivative? Our first derivative was this thing in highlighted yellow. So when you take the derivative, you bring the exponent down. Derivative of 4 is 0, so we can ignore that. What is derivative of this part? We bring the exponent down. That gives 2 times 3, 24, which is 648. And then your new exponent is negative 2 minus 1. That gives you negative 3 as your exponent. And so we write our second derivative as this. We plug in our critical point. Plugging in 9 gives us this number. You don't necessarily need to calculate it, but as long as you know if it's positive or negative, that's good. We know that this number has to be positive. So since this is positive, what does it mean for your second derivative to be positive? That means it looks like this. It's concave up. So since it's concave up, we know that yes, plugging in this L equals 9 did give us a minimum because it's concave up and it looks like a minimum. So the dimensions that would give us the least amount of fence is having a length equal to 9. What does that mean for W? So we said our W was 108 over L. So 108 over 9 is 12. So the dimensions of the fence will be 18 meters by 12 meters. And the total amount of fence needed is, what did we say the length of our fence was? It was 4L plus 3W. We now know what L and W are. So we plug those in and we get 72. Okay, any questions on this example? Okay, next example. So this one was also pretty interesting. So this was from a past or practice midterm, I think, in previous years. So it says, find the maximum area of the rectangle that can be inscribed in this right triangle with legs 3 and 4, and prove that it is actually the absolute maximum. So we're trying to find what area of this rectangle is the largest area that we could possibly inscribe. Like, will the rectangle be this area that will give us the most, or will it be this one that will give us the most? We don't know, so we have to find that out. So how do we find that out? And it says, hint, use similar triangles. So here I drew a bigger picture. We know that this is X and this is Y. Since we know this whole length is 3, what can we say this remaining part is? Well, it's going to be the whole length minus this Y part. So this orange part is 3 minus Y. What about this part? This part is the same thing. So you take the whole, we know the whole thing is 4, length 4, and we want to take out this X. So the purple part is just 4 minus X. Now, what are we maximizing? We're trying to maximize the area of the rectangle. So area of our rectangle is going to be x times y. But we don't want two different variables on our equation. We only want one variable. So how is it possible, like how are we going to get rid of one of the variables? So that goes into the hint for similar triangles. So for similar triangles, there's this thing where you can compare the dimensions of a small triangle and a big triangle. So how you compare them is you take this length of the small triangle, which is x. So this is our small triangle right now is this highlighted green triangle. So how do we compare them? We take the length of the small triangle, which is x, over the length of our big triangle, which is 4. So we have x over 4. And we set that equal to the length of the short side of our green triangle, which is 3 over y, over the length of the short side of our big triangle, which is 3. So this is how you compare similar triangles. We do x over 4 equals 3 minus y over 3. Now we can rewrite this so that if we multiply 4 on both sides, we get that x equals this. Now we have one of the variables equals something, and we can substitute that into our equation for area. So now the equation for the area of our rectangle, xy, we know what x is now. X is this. So we substitute that in and simplify. And now our area is just in terms of one variable, y. So that's, we wanted that. Area equals 4y minus 4/3 y squared. Now, what was the whole point of this? We're doing optimization. So you take the derivative of that, which gives you 4 minus, you multiply this down, it's 8/3 y. Now we want to find the critical points. So we set this equal to 0. Setting this equal to 0 gives us y equals 3/2. And so what does that mean for x? Well, we know the equation for x is this highlighted thing. So let's plug in y for what we just found is y. We just found y is 3/2, so we plug it in and we get x equals 2. So this means that the x and y that give us the largest area of our rectangle will be x equals 2 and y equals 3/2, which means that our area, our max area is 2 times 3/2. So 2 times 3/2 or 3. So the correct answer here was B for this question. Any questions on this example?
I have a more general question.
Yeah.
Is there any way you could quickly review what the first derivative test looks like?
Yeah, so the first derivative test, so what you do for the first derivative test is find the critical points. Then you make a sign chart. So if you found like critical points, here, I'll just do it for our example then, I guess. Where was, for this one, back here. So here we used the second derivative test, but instead we could have did the first derivative test. So first derivative test, we found our critical point was L equals 9. Then what you do is make a sign chart. So we put 9 here, and then you want to plug in other values into your first derivative. So plug into your first derivative. So let's choose like 0 is an easy number. That's smaller than 9. So if we plug in 0 to our, oh wait, let's not plug in 0. Let's plug in like 1. So what is f prime of 1? Well, you get 4 times, this would be 1 minus 81. So that gives you a negative number. 1 squared is a positive number. So this gives you a negative number over here to the left of 9. What about to the right of 9? Let's plug in like 10. So you get 100 minus 81. That's a positive number. 10 squared is also a positive number. So over here, you have a positive number. This tells you that the first derivative over here is negative. First derivative here is positive. So if it went from a negative slope to a positive slope, that means that it is a minimum. So it was correct. So the first derivative test is you want to use the sign chart and see if you have a change in sign. If you do, then you will have a relative max or min. For second derivative, you're just plugging into your second derivative and see if you get a positive or negative number. Does that make sense?
Okay, yes, thank you.
Yep. Any other questions on these optimization problems? Okay. All right, so then next topic is, I have some more examples, but let's do the next topic. So next topic was orders of growth. When do we use, it doesn't matter. You can use either first derivative test or second derivative test. Both should work. It's just sometimes one might be easier than the other depending on what you're more familiar with, but either works. Okay, so orders of growth. So a function, remember, is asymptotic to another function if you take the limit as x goes to infinity of one over the other and you get one. So if the limit of one of the functions over the other function equals one, then you know that f is asymptotic to g with this notation. What if you get that the limit is zero? That means that the function on the top grows more slowly than the function on the bottom. And so the notation is this double less than sign. Some notes about the asymptotic, which one grows slower, which one grows faster, that stuff. So you should remember that the higher the power is, it grows faster. So if you were comparing just x squared and x to the seventh, well, x seventh would grow faster because 7 is greater than 2. Also, exponentials grow faster than every single power. So if you were comparing x squared and e to the cubed, then e cubed would be faster. Also, logs grow slower, and also trig functions also grow even slower. So these are just some patterns to remember for when you're doing orders of growth things. A lot of it is testing back and forth, finding the limit between two different functions and seeing what you get. Okay, questions on orders of growth?
Can we do a practice problem or something?
Yeah, so let's see. There was, okay, where was, okay, let's just compare. So if you had natural log 2x and natural log x, in part A. So this is from some exercises, question 56. So you can take the limit of one function over the other function. You can try which one you want to take over or put on the top. So if we put natural log 2x on the top and then natural x on the bottom, then what does this limit give us? Well, we can, what is natural log 2x when you plug in infinity? That doesn't really make, it won't give you a number. So instead we can use L'Hopital's rule and we take the derivative of this. Derivative of natural log 2x is 2 over 2x. Derivative of natural log x is 1 over x. If we simplify this, so when you're dividing by fraction, you multiply by its reciprocal. So we get 2 over 2x times x. Simplify this, and this gives you 1. So this limit equals 1, so they are asymptotically equal. And because a property of being asymptotically equal, you could have done natural log x over natural log 2x instead, and you would have still gotten the same thing. You should still get it. It's 1. So if they're asymptotically equal, it doesn't matter which one you put on top or bottom. But if one is growing slower than the other, then that's where it matters which one you choose to put on the top or bottom. So for example, here we see like this one. So 1 minus cosine and x squared. 1 minus cosine and x squared. Again, we would get 0 over 0. So we have to use L'Hopital's rule. L'Hopital's rule says take the derivative of this top thing, which gives you sine x. Derivative of x squared gives you 2x. But then that gives you 0 over 0 again. So you have to use L'Hopital's a second time. Using L'Hopital's rule again gives you the derivative of sine is cosine. Derivative of 2x is 2. You get 1/2. This is not 0 and it's not 1. So we don't know if they're definitely not asymptotically equal, but we don't know which one will be slower than the other. We just know that they're not asymptotically equal. So this question would have been, are they asymptotically equal? Okay, any more questions on that part? Okay, so I have some like review of sigma notation and all the summation stuff. So some important summation theorems. We have the most common one where you're doing a sum of k. So you're doing like 1 plus 2 plus 3, etc. That's the most common one. We know the formula for the sum of that is how many terms you have times how many terms you have plus 1 over 2. Note that for n, how many terms you have, like what if you were starting at 2 plus 3 plus 4 plus 5, etc. Then you can't just say it's, you have 10 terms. That's not n. N here would be 10 minus 2 plus 1. You have 9 terms. So how you get the number of terms is you do like your last number minus your first number plus 1. That's for here if you have like, if they're increasing by 1. If you have the sum of k squared, this is the formula, etc. Summation rules is that if you're doing the summation of a constant, like sum from k equals 1 to 3 of 2, it's going to be, think about what that's showing. If k equals 1, k equals 2, k equals 3, no matter what, your expression is always 2. So you're just adding 2 every single time, which turns out to be 2 times how many terms you have, or 6. Similarly, if you have sum of a constant times a sequence, you can take that constant out. Or if you have the sum of 2 sequences, you can also separate them. So sum of the first sequence plus or minus sum of the other sequence. Now for finite sequences, we've learned 2 common ones, which are the arithmetic or the geometric. For the arithmetic series, the sum is always your first term plus your last term times how many terms you have, how many numbers you have, over 2. This is always the formula. And for geometric series, it's also always this formula. It's your first term times 1 minus what are you multiplying by, like the factor you're multiplying by, to the power of how many terms. This n is always number how many terms you have, over 1 minus r, which is your factor that you're multiplying by. So these are always the formulas that you use. But when you're using the formulas, you want to be careful because, and we talked a lot during this week of the recitation for this week, you can write these summations in different ways. So depending on how your summation is written, like this sigma thing of whatever, this thing, depending on how it's written, your summation formula might look a little bit different. But as long as you always remember, it's your first term times 1 minus factor to how many terms you have over 1 minus factor, it's the same exact idea. You just might have different subscripts depending on how you're writing your equation. So for example, if we were writing like from I equals 1 to n of this formula, this red thing is exactly equivalent to if you had written it in the purple way, where your I is starting at 0 now, and you're going to n minus 1, and you have a sub 0 of r. This exponent is now just I, not I minus 1. So they're written differently, but they're giving you the same sum. Because if you think about it, if we're doing like 10 plus 30 plus 90 plus 270, r is like what you're multiplying by. Because for geometric series, so geometric series always is like, say you're starting at 10. You multiply by 3, and you get the next term, which is 30. Then you multiply by 3 again, which is 90, etc. So your r equals, what are you multiplying by? Or in this case, it's 3. So if we wanted to write this sum using the red way, we would write it as you're starting at your first term, which is 10, times 3, because that's your factor, I minus 1. And if we're doing I minus 1, we should definitely start at I equals 1. Because when you plug in I equals 1, what's the first term you get? That's 10 times 3, 1 minus 1, or 10 times 3 to the 0. Anything to the 0 power is 1, so this is 10. So that indeed does give you our first term. And you would continue on, and you get the other terms. But what if we wanted to write it in the purple way, where we just have 3 to the I? Well, then when you find your first term, here you're plugging in 0 for your first term. So your first term would give you 10 times 3 to the 0, which is 10. And that does indeed give you your first term. So however you write your sequence, you can always double check to make sure that you're writing it correctly by plugging in these i's equals 0, 1, etc., and making sure that you get your correct sequence. Okay, and based on that formula, you can work out what the sum is. You should get the same thing. So both ways work. Any questions on finite series? I is like you're counting variable. So it's just like a counter. So like I is what you're gonna plug in here. So like in the red, for example, this summation, what this summation is telling you is, so this summation I equals 1 to 4, 10 times 3i minus 1. This is telling you like, what term do you get when you plug in I equals 1? What term do you get when you plug in I equals 2, I equals 3, I equals 4? When you plug in I equals 1, you get 10 times 3 to the 0, which is 10. When you plug in I equals 2, you get 10 times 3 to the 1. So that's 30. Here's 10. When you plug in I equals 3, you get 10 times 3 to the 3 minus 1 is 2. So that's 90. And etc. So you get 10 times 3 cubed, which would give you 270. So the i's are like when you plug in I, what term do you get? You get each term, and we're doing a summation. So each term, we're going to add each term. And so this summation from I equals 1 to 4 equals 10 plus 30 plus 90 plus 270. So the I is like you're counting, what tells you how to count. It's like a counter. Any other questions on this finite series? Okay, then we have infinite series. So there's also different approaches. We had the partial sum approach, and then the most common ones, geometric again, and then we have telescoping and harmonics. So these are the most common infinite series. So for geometric series now, we just saw geometric series for a finite number of terms, like if you just have 30 plus 60 plus 90. But Now for infinite, it's where if you have 30 plus 60 plus 90 plus 270, and you keep going, it never stops, goes to infinity. That's what an infinite series is. So for that, if you have that for geometric series, the rule here is that if your factor, the absolute value of your factor is less than 1, then your series converges. What does it converge to? It converges to this, a over 1 minus r. But if your factor is greater than 1, then your series will diverge. Oh, wait. Then the other common one is telescoping series. So telescoping series, when you see something like maybe like a fraction over another fraction, like if it looks like 1 over x minus 1 over x plus 1, something like that, you should be cautious and remember that that's the telescoping series. Like you have something minus something. And depending on whatever sum you're writing out, like I equals 1 to infinity, you can start writing out the terms. So let me write this as like i's. You can start writing them out like 1 over 1 minus 1 over 2 plus. That's for I equals 1. Plus, what do you get for I equals 2? You get 1/2 minus 1/3, etc., and you'll notice that all of the middle terms will keep canceling out. So the pattern with telescoping series is that the middle terms will cancel out. You'll be left with 1 minus 1 over some I plus 1. So you should, when you see telescoping series, you should write out everything and see what terms cancel out. And you get like the first term minus the last term. And then for harmonic series, you should know that it always diverges no matter what. Like if you have sum of 3 over n, that diverges. Sum of 9 over n, that also diverges. Okay, any questions about infinite series?
Wait, what does diverging mean again?
So diverging just means that the limit or your sum doesn't exist. So like this converging would mean that this equals some number, but because it diverges, it doesn't equal some number. So like the sum, like diverging means that your sum doesn't exist. Whereas
Okay, thank you.
Yeah. Whereas converging here, like here, this sum converges because we got that the sum equals 400. Okay, any other questions on sums? Okay, so let's move on to Riemann sums, which is another big topic. So everything about like area under the curve. You have like Riemann sums. I put it in the outline. So everything about, you have area under, like relating to area under the curve. We had started off with Riemann sums and trying to approximate those areas under curve. Then we learned all the actual techniques, like what is the integral of sine of x? What is the integral of x? So those were the charts, all the techniques like U sub, integration by parts, average value. Then we also had like area under some shaded region, and then improper integrals. So we have Riemann sum. So Riemann sum, the general idea was that you're given that you want to find the area under some curve from some interval a to b using n number of rectangles or trapezoids, like using 3 trapezoids, using 6 rectangles. How would you find the width of each shape? You take this interval, you take b minus a, and divide by how many shapes you want. And the length of its shape, depending on if it's a left or right Riemann sum, when you're doing rectangles, for the left Riemann sum, you would always use the left point to find that height. What is that y value? And use that as your height. For the right Riemann sum, you would use the right endpoint of whatever interval you're doing and use that as your height. Note that for trapezoids, when you're doing areas using trapezoids, usually it turns out that these widths that we usually use, that width will become your height in your area formula for a trapezoid. because the area of a trapezoid is base 1 plus base 2 times height over 2. So what are the base 1 and base 2? Those will be your heights, or like your y values that you get. And your height will be this distance in your x value, ln divided by 2. So for the trapezoid, you would find the area of each trapezoid, add them all up, that's your approximate area under the curve. So let's do an example. So this was from fall 2018, number 11. So it says, estimate the area under the graph of this between x equals 0 and x equals 4 using 4 rectangles and the left endpoint method. So what are the important points? We're going from 0 to 4. We want 4 rectangles, and we're doing the left Riemann sum method. So how do you approach this? So we have this function 36 over x plus 1 squared. Like, we're not sure what this looks like, but it turns out that it's not important whether or not we know what this looks like. We can just imagine it's some random graph. So I don't know what this looks like. I didn't graph it. I'm just drawing this curve just so that I can imagine, like, what components am I going to need to create the area of our rectangles. So this is some random graph. I don't know what it is. If we're imagining it from x equals 0 to 4, and we want 4 rectangles, well, then each rectangle, the width of each rectangle is going to have to be 1. So we're going to have 1 rectangle here, a rectangle, rectangle, rectangle. For rectangle 1, how are we going to find its height? Like, what height are we going to use? We're going to be finding what is the function evaluated at 0, because that's the left endpoint. So the area of our first rectangle will be, it's the width times height will be, what is the function at 0? So that's in the blue. For rectangle 2, it's going to be our width again, which is 1. What is the height going to be? Well, in this interval 1 to 2, what's the left endpoint? It's 1. So our height is going to be our function evaluated at 1. That's f of 1. And you keep going with the red rectangle and the purple rectangle. Now we know our function is defined by 36 over x plus 1 squared. So we can evaluate those at 0, 1, 2, 3. So that's what I did here. If you plug in 0 for x, you get 36 over 1, which is 36. So that's the blue. The orange is when you plug in 1, you get 1 plus 1, which is 2. So you have 36 over 2 squared, or 36 over 4, which is 9. So that gives you the orange, 9. And you would also similarly plug these in and get numbers. And it turns out you should evaluate it and get that. The area is 205 over 4. So the correct answer was D here. So notice how I didn't need to know what the graph looked like. I was just picturing this so that I can imagine, like, what components do I need to find this area? Like, what am I going to use for the height? What am I going to use for the width? Okay, any questions on this example? What if they asked for the right Riemann sum? Yeah, so you would do a similar process. So again, we don't know what the function looks like. So let's just say when using left. Yeah, so the pattern you'll notice is that when you're doing the left Riemann sum, we use like f evaluated at 0, 1, 2, 3. We stopped at 3. But for the right Riemann sum, what would it be if we use the right Riemann sum? So we need the area of the rectangle, the first rectangle. That would be your width, which is 1 times your height. What is your height going to be now? You're going to use, in this interval 0 to 1, what is the right endpoint? It's 1. So you're going to want to use the height for x equals 1. And that is f evaluated at 1. Then you're going to add area of the orange rectangle. What is the height going to be for the orange rectangle? Your right endpoint is 2. So it's going to be f at 2. F at 2. And then you'll get 1 times f of 3 plus 1 times f of 4. Oh, sorry. So this would be for right Riemann sum. So yeah, you notice the correct pattern that for left Riemann sum, we plugged in f at 0, 1, 2, 3. For the right Riemann sum, because we're starting at the right endpoint, we're going to be plugging in 1, 2, 3, 4. So yeah, and so for right Riemann sum, then you would continue evaluating this and get some number. You might get a different number than 205/4 though. So be cautious about that. Any other questions on this one? Okay, yeah, and you can always keep asking questions in the chat, and you can even direct message me if you don't want other people seeing, and I will see the message. Okay, so the next thing is we have, okay, my thing kind of got messed up, but this was the average over an interval. Not sure why it became like this, but the average over an interval is 1 minus b/a integral a b f of x dx. So if you have some function f and it asks you find the average over this interval a to b, then what that would be is you follow this formula. So average over an interval. So you follow this formula. Like if they ask, what is the average temperature from days 1 to 8? Average temp from days 1 to 8. And they like gave you a chart or they gave you some function that you have like 1, 2, 8. This is the day, this is the temperature. Okay, if they gave you the chart, you could like find the average. Okay, so let's pretend they didn't give you the chart and they gave you a function, a formula, f of t equals something, then you would follow this equation, this formula to find the average. So it would be 1 over 8 minus 1 times integral from 1 to 8 of whatever function you were given. And that should give you some number. And that's the average over an interval. Now, fundamental theorem of calculus, there's part 1 and part 2. It's not important which one you distinguish as 1 or 2. Some textbooks switch them, like this is 2 and this is 1. Just know it's fundamental theorem of calculus. So the first part says, how do you even find a definite integral? Like we know an indefinite integral, like f of x dx, will give you some expression in terms of x. But now when you actually put in numbers like to this integration sign symbol, then how are you going to evaluate that? Capital F is your antiderivative. So whatever integral you got, you plug in b, then minus your antiderivative with a plugged in. So that's how we know how to find the indefinite integral. The other part of the fundamental theorem of calculus gives you a shortcut way for if you needed to find the derivative of an integral. And this is important in one of the examples I'll go over later. Yes, okay, so if we find the derivative, if it asks for the derivative of some integral, what you do is it's going to be exactly the same function as you have in here. But if this bound over here is more complicated, like if it's not just x, if it's say x squared, then it's kind of like a manipulation of the chain rule where you have to plug in this weird bound into your function and also multiply by the derivative of this weird bound. But if this top bound was just, for example, y, then here we see the derivative of this integral is you literally just put in y where you see x's. So wherever you see an x, just put y. It would be sine y over y. But if this was the derivative of y squared 18, sine x over x, then what would this be? Wherever you see an x, you want to plug in y squared. And we also have to multiply by the derivative of y squared, which is 2y. And yes, I see your question in the chat. I'll do that at the end. Okay, any questions about these concepts?
Why did it become y squared?
Y squared. Oh, this was a separate example. Example 3. Like if one example would be if they ask you this, the answer would be sine y over y. Then completely separate, if they ask you this question, then the answer would be this.
Okay, thanks.
Yep. Any other questions? Okay, so we went over it. For indefinite integrals, also don't forget the plus c. I know a lot of points were taken off, or like 1 point was taken off of past quizzes for not having this plus c. Definite integrals, we would use the fundamental theorem of calculus, where you have your antiderivative with b plugged in minus antiderivative with a plugged in. For integrals, you should also know, so there's properties of like linearity. You don't always, if you're already comfortable with integration, you don't have to always take out this scalar, but sometimes it is helpful to take out this scalar so that you can focus just on finding this integral of whatever function you have. Also, if you have the integral of a function plus another function, you can always separate them. So integral of the first function plus integral of the second function. And there was a quiz problem like this where, actually I have an example later. There's a quiz problem, past quiz problem, where there's like an integral of something plus something plus something plus something. And that looks very overwhelming, but you can think of each thing separately. You can think of it as the integral of this first thing plus integral of the second thing plus integral of the third thing, etc. So it turns out to be a simpler problem than if you're just like, what is this integral of this plus this plus this? Yes, so did you say there was a practice problem where we have to use the fundamental theorem part 2 that you went over? Yeah, someone brought it up in the fall 2012 exam. There was one problem where this was useful, I think, and I will also go over that at the end of this session. So as I was going through like past exam questions to prepare for this, I saw a bunch of like nice exam problems, which I just like started adding them, but I couldn't fit them in my review notes, but they were also some nice examples. And this one was a nice example. So fall 2012, number 3, but we'll go over that at the end. Okay, or should I we'll go over at the end. Okay. Yeah, and I'll also like post those like nice problems also, because I think they're kind of nice to look at. Okay, so then we have the integration summary. So this is this big chart. If you have another chart from the textbook or anything, make sure you know all the common integration like trig, e to the x, inverse trig, all of those. And you can write them on your cheat sheet also. Integration techniques, be comfortable with use substitution, integration by parts, and sometimes tabular integration is also very helpful. So for use substitution, the idea always is that you're going to pick some u. What will u be? U will usually always be if you find something like, if you have an integral of, and you see like a parentheses to some exponent, and you see some complicated thing here, u might be this thing in your parentheses. U is also commonly whatever's under your square root, or how else do you find u? You want to pick a u so that its derivative you can find somewhere else in your expression. So once you see a bunch of problems, you'll see, oh, what is commonly used for u? Usually use like something in your parentheses or something in your square root, or maybe something in your like sign of a complicated thing. Oh, sorry. Sign of whatever complicated thing is in here will be your u. But make sure that its derivative, of course, is on the outside. Then you take its derivative and you want to substitute everything in your integral so that it only has u's and du's. You don't want any other variable in there. That should make things simpler so that you can integrate and then like integrate a nicer function. And then once you integrate it, you want to plug back in what u was so that now your answer should be in terms of x or whatever variable you originally had. I want to note that when you're finding du and you're like substituting things back in, we would say like, say du was 1/2 dx. And what was left over in our equation just had a dx. Then what we would do here is you multiply by 2 so that you get 2 du equals dx. So we're allowed to do that. You can multiply by scalars and divide by scalars, but you can't multiply by variables. So if there is like an x dx here left over, if you had an x dx here in purple left over, you can't just say, oh, 2x du equals x dx. You can't multiply or divide by variables. You can only do that for scalars. And also you can't add things. You can't be like 2x plus 3 du equals x plus 3 dx. Like if you had if here what was left over was like an x plus 3 dx. Sorry, I don't know why it keeps doing that. Yeah, so you can't multiply by variables or add things. Integration by parts, I like this highlighted formula. It's easier to remember. You just remember uv minus integral b du. How do you choose u? You can use this LIATA, so LIATA acronym. If you see any logs, that's the first thing you want to choose for u. You see inverse trig next. Algebraic is like polynomials. So like if you see an x squared plus 3, maybe choose that. That might be a good choice for you. Then trig and exponential. So you go down the list of what do you want to choose for you. Also careful that I mentioned yesterday in the review session, integral of natural log x is not 1/x, by the way. You have to use integration by parts in order to find this integral. Okay, any problems on, any questions on like the overview before we do integration examples?
Can we do the example with like the integration sign, integrate ln of x using integration by parts?
Yeah, so okay, I'll also put it here. Okay, so it's also in yesterday's review notes on one of the pages, in the multiple pages, but I can do it again. So what is the integral of ln x dx? We need to choose a u. What does our LIATA say to choose for u? Do we see any logarithms? Yes, we see a natural log x. So that's the first sign to us that we should choose u equals ln x. So u equals ln x. Everything else is dv. So dv is everything else. What's left is just dx. dx is the only thing that's left. Now, for our formula, we need all the components. So we need du, and we also need v. What is v? What's the integral of, you can imagine there's a 1 here. Integral of 1 is x. And you can check that because what is the derivative of x? 1 dx. Now, u is natural log x. We know the derivative of natural log x. It's 1/x dx. So yeah, this is 1/x is the derivative of natural log x, but it's a unique one where it doesn't go the opposite way. Like the integral of natural log x is not 1/x. So wait, so integral of natural log x is not 1/x, but integral of 1/x is natural log x. So if it's not in our chart, then you shouldn't assume like backwardsness. Okay. So now we have all our components. Integral of u dv equals uv minus integral v du. Now we plug in what we found. So u was natural log x, v was x, minus integral of v is x, and du is 1 over x dx. Now, when you get to this point, you see this integral. Some people might think, oh, there's an x and there's a 1 minus x. And maybe you have to do integration by parts again, because this looks like two separate functions. But keep in mind that this simplifies because the x's cancel out. So this simplifies to integral of 1 dx. So that was another common mistake on the quiz 8 or quiz 9, quiz 8 or quiz 9. So make sure you simplify everything first before you do any techniques. So here it's simplified to 1 dx. So we have x, natural log x. What is the integral of 1? That's x. So our final integral is this, plus c if it's a definite indefinite integral. If it's an indefinite integral. Any questions on integral of natural log x?
No, thank you.
Yep.
Quiz 9 scores are going to come out.
Can you repeat that? I think your sound is. Wait, did someone? Okay, or no? Okay. If you figure out this sound, just like unmute anytime. Okay. Let's try this example here. Oh, do you know when quiz 9 scores are going to come out? Soon, definitely before the final. So you'll hopefully get them before the final and the redo quiz. Yep. Okay, so this is from fall 2018, number 12. Okay, so we look at this integral. This is L. L equals 36 over x plus 1 squared. Okay, does anyone want to put in the chat or say, what do they think we're going to use to solve this? Like what technique stands out to you? Or
Substitution?
yeah, u sub. Because we see like something in parentheses. So that gives you a hint like, oh, maybe the thing in parentheses is going to be our u. Right? Okay, what about this one? What do people think we're going to use for this? So you could either like trial and error, find what the integral of e to the 2x is, because we know that the derivative of e to the, we know that the derivative of e to the 2x will end up being 2e to the 2x. So what about the derivative of 1/2 e to the 2x? That would get rid of that 2, and the derivative would become e to the 2x. So you could trial and error it and see that the integral of this will be 1/2 e to the 2x. But the more proper way to do it would also be u substitution. So let me explain. Let's look at L first. So L is this integral. Let's choose u equals x plus 1. So du equals dx. We want to plug in u's and du's. So this x plus 1 was here. It becomes u squared. Dx was just du. And now I like to write them as like move this exponent up so that it's u to the -2. That way we can take the integral more easily. Because how do you take an integral? You add 1 to the exponent, which makes it -1, and you divide by that new exponent, -1. That gives you -36 over u. But you make sure that you're not plugging these numbers in when you have a u. You want to make sure that your integral is fully the integral first, then start plugging in your numbers. So remember, we don't want u's here, so we replace u with what it was, x plus 1. Now, using fundamental theorem of calculus, part 1, we can plug the numbers in. So we plug in 4, and we get this, minus plug in 0. Get this, simplify, and you get 144 over 5. What about m? So m, similarly, we don't want this like this is complicated, right? We know the integral of e to the 1 variable. Let's make that u so that way we know what the integral of e to the u is. So u is 2x, du is 2 dx. So But what is left over? We only need this x left over. So I divide both sides by 2 to get 1/2 du equals dx. Now I substitute everything in so that there's only u's. So e to the u, dx was 1/2 du. Now what is the integral of u? That's our favorite integral. It's just e to the u again. But what was u? U was 2x. So make sure you plug back in that 2x. Now this is the full integral of our original question. So now we can plug in our numbers. Evaluate it at natural log at 6 minus evaluate it at 0. When you're evaluating this highlighted part, you want to be careful because we know e to natural log 6. So you always want to put the natural log next to the e because this trick only works if you have e natural log like right next to each other. E to the natural log 6 by the inverse property from yesterday's review session, this is 6. So we have 6 squared, which is 36. That would have been different from if you had done like 12, or if you had gotten like, I don't know, like 2 times 6 or anything else. So be careful when you're simplifying that, and you get 35/2. So L equals that, M equals that. What was the original question asking for? It was asking for L times M. So L times M is 504. So the correct answer choice was E, 504. Any questions on these two integrals? Okay, so here I have an example that was similar to the quiz where you have they give you the derivative. You want to find f of x. How do you find f of x? You take the integral of this derivative. So you take the integral of all of this. I added this 1/x just to add in another trick here, because one of the things was that integral of 1/x squared or x negative 2, you can use the regular integral rule where you add 1 to the exponent and divide by -1. The only time where you can't use that rule, like where you just add 1 to the exponent and divide by it, is if you had 1/x. Because 1/x specifically, this integral is natural log x. Because if you did 1/x is x to the -1, if you use the normal integral rule where you add 1 to the exponent, you get x to the 0 over 0. That's a problem because you can't divide by 0. So the only time where the normal integral rule doesn't work is if you have 1/x. That integral is specifically natural log x. Okay, so you can work out all of these and see, I will post these notes later, but you can work them out and you'll get the final answer. And I also did another problem. So one of the comments on recitation notes was that you guys wanted more examples. So lots of examples, but we have a lot of more topics. So let me move on to area of shaded region. Okay, but any questions about integrals before I move on though? Okay, and you can check out these examples. And if you don't get them, I have lots of office hours later in the week that you can come and ask oh, page 27 of the notes. Can you explain? Okay, so area of the shaded region. This is from fall 2012, question 12. It says, find the area of the shaded region. So in past quiz problems, they just gave you what interval you're going on. But I like this example because they don't give you the interval that you should integrate on. Like right now, you should identify that. How do you find the area in this shaded curve, the shaded region? You would do this top function, integral of the top function, which is sine 2x, minus the bottom function, because that's how you get the shaded part. You did this top function minus the bottom function, cosine x. But then what are these numbers here? What do you put here? Like in the red. You need to know what this point is and what this point is. So one point should be more clear. This point should be clear. Why should this point be clear? Because this red line is cosine x. Cosine x, we know cosine of 0 is 1, so that's correct. And it goes down, and if you travel on the unit circle, where do you get cosine equals 0? You get it when x is pi over 2. So this point must be pi over 2. The only other point where cosine of x equals 0, it's only when x is pi over 2 or x is 3 pi over 2. But that would mean that, so if this was your graph of cosine like this, that 3 pi over 2 would be over here. We don't have the rest of that graph. We have, where is the first point where cosine x is 0? That's when x is pi over 2. So this point here, we know the n number must be pi over 2. But what is this first number? How do you find it? To find that, you want to know where these two functions intersect. Where do they intersect? So we set them equal to each other. Cosine equals sine of 2x. That way we can find where do they intersect. Now, you're looking at this and like, how do you even solve that? Like, it looks weird. Well, you need to know the trig identities in order to solve this, because otherwise you have cosine x equals sine of 2x. You might be able to like plug in numbers like test x equals 0, x equals pi over 3, etc. And you might get the answer, but in case it's more complicated, it's also helpful to know trig identities. So if we subtract cosine on both sides, we get 0 equals sine of 2x minus cosine x. What is sine of 2x? By the double angle identity, sine of 2x is 2 sine x cosine x. Now we can factor out this cosine x. So we get cosine x times 2 sine x minus 1. Great, that looks better because now we have something times something equals 0. How do we solve that? It separates into two parts. We have the first something equals 0, and you get set the other thing equal to 0. We have cosine x equals 0, and this 2 sine x minus 1 equals 0. What do you get from here? If you add 1, divide by 2, sine of x equals a half. When does sine of x equal a half? That's when x equals pi over 6. How do I know that? Because you could do x is inverse sine of 1/2. Inverse sine is only defined on from negative pi over 2 to pi over 2. Like if you think of the unit circle, inverse sine is only defined on this highlighted part. When does sine a half? That's around like this purple right here, which is pi over 6. And when does cosine x equal 0? Again, that's when x equals pi over 2. Pi over 2 was the point we already knew about over here, like where they intersected. Pi over 6 is this other point that we needed to find. So now we know our interval. We're finding the area under the curve from pi over 6 to pi over 2. So this is our integral, sine of 2x minus cosine x on this interval. How do you solve this? You can think of the two integrals separately if you want. So like I did the green part minus the orange part. How do you find the integral of sine 2x? Again, because it's a trig of a complicated thing, like in this parentheses, it's most likely that you're going to want to use u substitution. Specifically, the u that you're going to pick is this, whatever's in this parentheses, most often, most of the time. So if we pick u equals 2x, solve, etc., we get that the integral is negative a half cosine 2x. And over on the orange side, the integral of cosine x was sine x. Then you want to plug in your values. So the green thing evaluated at pi over 2 minus green thing evaluated at pi over 6. Same thing with the orange. You can simplify and you get 1/4. But the main important takeaway from this problem was, how did you find those? What interval are you integrating on? And the fact that you're doing this function minus the bottom function. Okay, any questions on this problem? Okay, so here I also added a random slide in the middle, but some trig things you might need to know. So you saw how in the last problem, I've used what was inverse sine of 1/2. I needed to use this, like, where is inverse sine of x defined? Well, the answer, or what were we doing? Inverse sine of 1/2. We knew that the answer would have to be within like pi over 2 to pi over 2, like some number within this interval. So you should know the unit circle. Like if it said, what is sine of 30? Sine is always your y value. So sine of 30 is 1/2. What is cosine of 2 pi over 3? Cosine of 2 pi over 3. Cosine is always your x value. So 2 pi over 3. We head to 2 pi over 3. What is the x value? -1/2. So it's -1/2. Same with inverse trig. How do you do that? You should make sure that whatever answer again is on the correct range. So if they said, what is inverse cosine of 1/2? Well, inverse cosine, your answer should be within 0 to pi. So somewhere on this highlighted part. Where is the x value equal to 1/2? Let's see. X value equal to 1/2 right here. So this is pi, and what angle is that? Pi over 3. This angle. So that's how you do inverse trig. And also double angle identities, the even odd identities, those are useful for finding when a function is even or odd. Pythagorean identities, this is the most well-known one, sine squared x plus cosine squared x equals 1. You can get the other two by either dividing sine squared x or cosine squared x from the original. And the sum difference identities also. Any questions on the trig stuff? Like, fine, make sure you know, I know some people ask like how you do inverse trig. So if it had a question like find the integral of, let's see, find it 1 over square root 1 minus x squared. 1 minus x squared from like some number to some number, you would find that it's inverse sine x evaluated at that number and that number. So when you evaluate it at whatever number this is, you should know these rules. Okay, yeah, other questions on trig review? Okay, so then we have, where is negative pi over 2? Negative pi over, so pi over 2, starting from 0, you travel pi over 2, that's 90 degrees. So negative pi over 2 is if you go the opposite direction, 90 degrees. So negative pi over 2 is here. Is this angle. The same, so like this is pi over 6. Yeah, negative pi over 6 would be this. Okay, so negative just means you go clockwise, the opposite direction. Okay, so here I have another example, find the area. Let me just give an overview of this. When you're doing the integral of x squared, square root of x squared plus 9, you should recognize that, oh, we're probably going to be using a u substitution here because we have a square root. And it's convenient that, imagine if we chose u equals x squared plus 9, that derivative is 2x. And what's left over is this x here. So the idea for this was u substitution. And in order to solve this, you will need to use u substitution. Okay. Yeah, any questions on area of shaded region? Things? So a lot of times when you're doing the area of a shaded region, like you're doing an integral of something. For integral of something, you might need to use the different techniques, like use substitution or integration by parts. Okay, but let's do improper integrals. So improper integrals are where you see like an infinity as one of the bounds. When you see infinity as one of the bounds, you want to think, got to do limit. So here we do limit of choose some variable going to infinity from a to where was infinity? It was up here. So let's put that variable there of f of x dx. So you evaluate this, you should have something in terms of with b's in it, and you take the limit. And the same, and these are the other rules. And the idea is that if the limit exists, or if the limit converges, or if the limit equals some number, then your integral will have also converged. If your limit, you found that it does not exist, then your integral also diverges, does not exist. Same for discontinuities as some number. So sometimes when you plug in a number, you get like undefined. And so you will also need to do some limit rules for that. Then for improper integrals, a common thing is on convergence. So convergence, there are some common rules. So there's like a table in the textbook of some common integrals, improper integrals, and what are their conditions for convergence. So if you're just in general, the integral from some number to infinity of e to the kx, this converges if k is less than 0. So if you have a negative, like e to the negative x, e to the negative 2x, that will converge. And how you can prove that is you can literally find this integral using the improper integral like definition and solve it out. So I will leave that as an exercise, but you will find that this only converges if k is less than 0. Another popular one is the p series. So if you ever see like 1 over x to the some exponent, or integral from e of x to some negative p, well, that would be a different rule. But like if you see a variable to some exponent, then this converges if that exponent is greater than 1, or diverges if that exponent is less than or equal to 1. And here's the chart. So all of these are types of integrals and conditions for convergence. When do they converge? For this last one, you can also prove this by actually finding this integral by doing the limit, etc., taking the integral. You'll see that it converges when q is less than -1. And so these were just, how do you determine if an improper integral converges? These were the common ones, e to the x, the p series, this. Another strategy is to use comparison test. Comparison test is where you find another function that is more common, that you're more familiar with, that you know if it converges or diverges. Then you compare that familiar one to the one that they're asking about, and you either follow path A or path B. And depending on if these conditions are held, then you'll know that if your like complicated one also converges or diverges. Okay, so I will do an example, but any questions on the concepts behind these? Okay, so this is a tricky one that I found. If you're trying to find the integral from 0 to 3 of this. So say you start off normally, you're finding the integral. So we can, okay, this you would use substitution. I skip use substitution. And this integral turns out to be x minus 1. You add 1 to the exponent, so 1/3, and divide by that new exponent, 1/3. So this integral gives you 3 x minus 1, so 1/3 from 0 to 3. And you're like, okay, nice. But it turns out that at x equals 1, if you plugged in x equals 1 here, what would you get? You'd get 1 over 0. So at x equals 1, our original function is undefined. How can you take an integral when one of the points is undefined? Like, how would you even find that integral or find that area under the curve? So we have to split this integral into 2 parts. We have to, the point that we're going to split it at is this discontinuity at 1. So we're going to do the integral from 0 to 1 of that, the same function, plus the integral of that function from 1 to 3. This way, because we know that it's a discontinuity at 1, so we're going to make that our limit point. Like we're going to do limit from b going to 1 of the integral. And the same for the green, except this 1 is at the bottom, so I'm going to call it a. Now we can take the integral properly. What is this integral? It's 3x minus 1 to the 1/3. And we're going to evaluate it at b. So I plug in b, we get b, and then minus plug in 0, which is -1. So looking at the orange, we get, what is this limit of the orange as b goes to 1? You plug in b equals 1. When you plug in b equals 1, you get 1 minus 1, which is 0. That's 0. Over here, -1 to cube root is -1. So you have minus 3 times -1. So that gives you 3 in the orange. What about the green? So the green, you do the same thing. We find that this integral is this, but now we're plugging it in at 3, then subtracting, plugging it at a. So we get this, and now we're doing as a goes to 1. At this point here, you again see plugging in 1 gives you 1 minus 1, which is 0. And then this is 3 times 2 to the 1/3. So we'll just leave that green thing like that. And that's your final answer. So this is the correct integral of the original question. Any questions on this problem? Okay, so then what about, does this converge or diverge? E to the negative x squared. Oh, this should be dx. Well, we know from the chart above that I talked about where that e to the x converges when k is less than 0. So when you're approaching this, okay, your first step might be, okay, let's take the actual integral and let's do like limit as b approaches infinity of b1 e to negative x squared dx. Oh, sorry. But how do you take this integral? Like if we started off with maybe u substitution, let's pick like u equals x squared, du equals 2x. But we don't have any x's left over in our expression. We don't need this x. So how would you can't do this by u substitution. We don't know how to take this integral. So then you get stuck. So you're like, okay, maybe try comparison test. So comparison test, let's compare it to something we know. We know that e to the negative x converges by our rule from the chart. So following path A, since g of x converges, we need to know, is f of x less than or equal to g of x? Let's check. So what is f of x? That's our complicated thing, e to the negative x squared. G of x is our familiar function, e to the x. So is this less than this? How do we know? Maybe let's try like rewriting it. This negative exponent, let's get rid of the negative exponent by bringing it to the denominator. Same over here. Now we cross multiply. So this gives us e to the x. And cross multiply over here. This gives e to x squared. Now, is this true? Yes, because e to the x squared is going to go faster down. Like e to the x, or faster up. So it will be a greater number. Okay, you can even test it. Like at x equals 1, the blue gives you e. Green gives you e, sure. But at x equals 2, now the blue gives you e squared. The green is now e to the 4th. That's a way bigger number. So we know that this is true. So by the comparison test, f of x, or our e to the negative x squared, does converge. Or sorry, this integral converges. I should write integral converges. Any questions on this problem? Okay, so then another example. So again, you're encountered with this integral. Your first step should be trying the improper, like the limit way, doing limit e to 1, but how do you even take this limit? Like or take this integral, like you're confused. Will you ever have to do, yeah, it can be used actually. I did see, wait, let me see if I can find that example. This was a really good example actually. Aha, yeah, okay, let me do this example and I'll answer your question. So you find this limit, but how do you even take the integral of sine squared x squared? Like you're confused. So let's try comparison test. Compare it to something that looks familiar. Let's forget about this like sine squared. We know 1 over x squared, that looks nice. That converges by the p-series rule. So now following path A again, is f of x less than g of x? Let's check. Is this sine squared x over x squared less than 1 over x squared? Cross multiply. Then you get this. Is that less than or equal to x squared? Well, we know from the unit circle. Imagine the unit circle. Sine x is always going to be between 0 and 1, no matter what. Can't get a higher number. You can even imagine the graph of sine x. Looks like that, whatever. With 1, even -1. The highest number you can get is 1. So you know that, say, like this x squared is going to be multiplied by some fraction. So that has to be less than just that number itself. This is true. So by the comparison test, our complicated unknown thing does converge. Any questions on this example? Okay, so we had a question in the chat. Will you ever have to do asymptotic analysis when doing comparison tests? So I did see an example of doing this. So if you had f of x equals, it says like converge or diverge this. 1 over square root x plus 1 dx. So you see this integral. Maybe you try doing it limit way, limit b going to infinity. But then how do you even take this integral? Use substitution, you end up with an x in your derivative. You don't have any x's left over. How do you do integration by parts? Like we don't even know how to take this integral in the first place. So it doesn't work. Let's try comparison test. So what's something that looks nice? Well, this 1 over square root x looks nice. Let's pick that as our familiar thing. 1 over square root x. What is that? That's 1x to the 1/2. By the p-series rule, this diverges by the p-series rule. Or by the p-series rule or p-test diverges by p-test or p-series. Now path A, so it diverges by the p-series test. So you said, can we do asymptotic analysis? If we did asymptotic analysis, what does asymptotic analysis say? Well, if we get that the limit as x approaches infinity of something over something equals 1, then they are asymptotically equal. Meaning that we know that g of x diverges. So if we end up getting that this limit equals 1, that means that this function is asymptotic equal to g of x, which means that this should also diverge. Because if they're asymptotically equal, like if they're similar, they should both diverge as well. Right? So let's try it out. If we limit of our complicated 1 over square root x plus 1 over what we know, what does that give you? That gives you limit as x approaches infinity of square root x over square root x plus 1. By the limit going to infinity rules, the degree of the numerator equals the degree of the denominator. Since the degrees are equal, that limit is their coefficients. What are the coefficients? There's only a 1 and a 1. So this does equal 1. They are asymptotically equal. So our complicated thing, f of x, does also diverge because they're asymptotically equal. So yes, there are cases where you can do this asymptotically equal, like the orders of growth thing, which is why we learned it at the very beginning also. Any questions on this problem? What is the p-test? So p-test or p-series. So p-series was up here where I said like the common convergence rules. The common ones are this. So you should cite like, oh, we know this integral converges if x is less than 0. The rule we just used was the p-series rule, where if we have this improper integral of 1 over x to the p, this always converges if this p is greater than 1, and it diverges if this p is less than or equal to 1. In the example we just had, we did 1 over square root x, or 1 over x to the half. 1/2 is less than 1, so that's why it diverged. Any other questions on that example? This example? Or improper integrals in general? If the p-series test is sufficient enough to determine, only if it's, okay, like if they just asked you like 1 over this of 1 over square root x, then yes, it's sufficient enough to say this diverges by the p-series test, or by p-series, or by p-test. But if it's something more complicated, like that it doesn't look exactly like the rules I listed above, then you can't just say by some test. You should do the comparison test or something else. Yeah. Oh, by the way, the question was, is the p-test sufficient enough to determine if an integral diverges or converges? Okay, so next topic, we have like most recent things were probability density. The thing you should know about probability density is that in order for it to be, for some function that you're given to be a probability density, it means that if you take the integral from -infinity to infinity, you should always get 1. So if it gives you like f of x is like cx squared or something more complicated, then what you're going to do, and it asks you to find c, then what you do is you do this integral, of cx squared, and you set it equal to 1. You find out what is this integral, this highlighted part, find that, divide it, and you'll get c equals 1 over something. Or whatever this is, and you simplify, do some algebraic step, find what c equals. Once you know that it's a probability density function, you can find the median. And this was on the redo quiz, I believe. So the median is some number m such that you could do this integral. So the integral from that median number to infinity should be 1/2. Or you can do the other way, like the other half. Why is that? Because think about the median. The median is like your middle number. So if the median is your middle number, then the area under curve all to the left should equal the area under curve all to the right. Like that's what it means to be a median. Okay, and for mean, this is also a formula. You do this integral of x times f of x. Variance, now you just have this extra part, x minus mu squared f of x. Standard deviation is square root of your variance. Okay, questions on probability density. These should all be formulas, so you can follow them. Sometimes these integrals may also be difficult, so you can use substitution or integration by parts. Okay, so then last topic was Taylor series. So Taylor series, this is the formula. If it asks you, find the Taylor series of sine of x centered at x equals a, some number a. Then the process that you're going to do is you write down f of x, its derivative, its second derivative, etc., however many you need to go. Whatever a is, like that number a, you should evaluate each thing at a. So evaluate f at a, evaluate that first derivative at a, evaluate the second derivative at a, etc. Now you have all your components and you plug them in, because now we just found what f of a was. Plug that in. We know what the first derivative evaluated at a was. You plug that in, and etc. You keep plugging it in to this formula, and you should get something. That's the Taylor series centered at x equals some number a. Now, specifically, if that number a is 0, that's what they call a Maclaurin series. That's the Taylor series generated by f at specifically x equals 0. And the most common Maclaurin series, that like the big 4 that are used, are sine x, cosine x, e to the x, and 1 over 1 minus x. Those are the most common ones. I also added a natural log one, which I've seen come up recently also. But these are the main ones that I would recommend, like writing on your cheat sheet or something in case Maclaurin polynomials come up. If you don't memorize them, it's also okay, because as long as you know how to derive them, which is the same process that I wrote up here, it'll just take some extra time. Okay, and how you manipulate. Did Rimmer say on Rimmer's, like, let's see, did he say he put like the rules on this website? Said two-sided cheat sheet, so 2 sides. Oh, the question was, is it double-sided, the cheat sheet? So Rimmer says it's 2-sided cheat sheet. So I'm assuming one paper, 2 sides. Okay, and if it asks you for like first, okay, question. If it said find second degree Maclaurin polynomial, what is the exclamation mark? That's factorial. So sine x. So the question, what is the exclamation mark? So exclamation point means it's called the factorial. So for example, 2 factorial is you go 2 times 1. So you go from whatever number times all the way down to 1. So like 4 factorial is 4 times 3 times 2 times 1. 9 factorial is 9 times 8, 7, 6, 5, 4, 3, 2, 1. 1 factorial is just 1. 0 factorial is weirdly 1. Okay. Does that make sense? Yep. Okay. And so if it asks you, so for example, find the second degree Maclaurin polynomial of sine of x. We know what the Maclaurin series for sine of x is. It's this. What does second degree mean? It means that the highest power or highest exponent you want should be 2. So if you wrote your answer to this as x minus x cubed over 3 plus x5 over 5, that would not be correct, because you're going above 2 degrees. Like you have an x cubed, you have an x5. You don't want that. So this x to 5 term, that's too high. X to 3 term is also too high. So the answer here would just be x. Because that's degree 1, that's less than 2, that's great. What if they said, fine, now, and it goes into, you can manipulate all these Maclaurin series. You can multiply Maclaurin series, divide them, do other manipulations. So what if they said like, find, find 6th degree Maclaurin polynomial of sine of x squared. What do you do then? So our original Maclaurin series was x minus x cubed over 3 plus x to 5 over 5, etc. Now it's sine of x squared. So in our original thing, we were plugging in x's, but now it's x squared. So the only difference is that wherever you see an x, you want to put x squared instead. So here I see an x, I'm going to change that to x squared. Here I see another x, I'm going to change that to x squared. Here I see another x, change that to x squared. What does that give me? That gives me x squared minus x to the 6 over 3 factorial plus x to the 10th 5 factorial. The question asks for 6 degree. This is 10, that's too high. We don't need it. X to the 6, that's fine. That's going to 6 degree. The answer would be x squared minus x to the 6 over 3 factorial. Yeah, let's go over that. So, okay, any questions on Taylor series on this stuff?
Yeah, I had a question. Are like combination Taylor series of known as like combining like e to the 3x times like sine x squared and then making that polynomial?
Yeah, are you asking how to do it?
Yeah, like can
Yeah.
we see that on the exam? And could you show an example, please, of like a difficult one?
Yeah, let's do an example. So, find, let's also do like, okay, we'll find out how many degrees I want to make this. But let's do like e to x sine of x for now. Okay, wait, let's make it interesting. E to the x sine of x squared, right? We know e to the x, so I'm just gonna copy this that we know of. Okay, so facts that we know e to the x is this one. We just found sine x squared is this one. Or like, let's continue, whatever continue it is, dot, dot, dot. What is e to the x? What's the Maclaurin series for e to the x times sine of x squared? That means that you have to do the Maclaurin series for e to the x. So this plus dot, 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 multiplied by what did we find for sine of x squared? So this is x to the 10th over 5, etc. So let's say we want to find the 8th degree. Okay, so what do? We have to, this is just like multiplying any ordinary polynomial. You have to FOIL. So we start with the 1. We go 1 times x squared, that's x squared, plus 1 times this second term. So that's, oh, that's minus x to the 6 over 3 factorial. Now, if we did one more, we get 1 times this x to the 10th. That gives you x to the 10th. But remember, we're stopping at 8. So we don't even need to write that. You don't need that last FOILing part. Okay, so that's just FOILing this. But we didn't FOIL the other terms. What about this x times x squared? That would give you x cubed. Then this x times the next one, that would give you minus x to the 7th over 3 factorial. The next one would give you x to the 11th. That's going overboard. We don't need that. So stop there for the orange. Okay, what about over here, the third term? We have x, the red. So we have, that would give x to the 4th over 2. Oh, sorry, my pen is, that gives x to the 4th over 2. Then this gives plus x to the 8th over 2 times 3 factorial. Okay, and if we did one more, that would give us x to the 12th. We don't need that because remember we're stopping at 8. Okay, what about over here? Okay, maybe I shouldn't have done 8, but okay, so here x cubed would give you, so the purple is giving you x to the 5th over 3 factorial. Then the next one gives you x to the 9th. Okay, that's overboard. We don't need x to the 9th. So let's stop with the purple. Okay, and then, so it turns out that for e to the x, if we continued writing this x to the 4th times x to the 2 would give you x to the 6. So we could keep continuing that. continuing that, and you would need to continue with, so you would want to go up to, let's see, x to the 5 would still work. Okay, this is getting, x to the 5 plus x to the 6 over 6. So you would stop at, so you keep doing the FOILing thing for each thing. And the last term would be this x to the 6 over 6 factorial times x squared. Because then once you go over, you get x to the 12. So you would keep continuing. I made it too much, so I won't continue it. But if you see, do you see the idea here? Keep going. Do they want us to simplify the denominator and multiply out the factorial? If it's like a low number, like 3 factorial, then yeah, you can, 3 factorial is just 6. It's 3 times 2. But if you're worried about making like algebraic mistakes, maybe just leave it like as is, unless they say like simplify as much as possible, because we'll probably still accept with factorials. Yeah. Okay. Yeah. Questions on this one? This example? Okay, yeah. So that was the end of like the prepared notes for the rest review session. So now it'll just be like free office hour time for questions. Okay. Okay, so let me see. Okay, wait. Before I get to the question about prep quiz 2, I know I told someone I would. Oh, and there's a question on 2013 final. Where can you find my notes? On my website? They're right here. So I will, the schedule's on here, and the notes, like yesterday's notes, are here. You could click the link there and it'll pop up. And the recording from yesterday is also there. And this link, do I have my, I can also put it in the chat if I can get to it. Yeah, everything's on my website, all the notes, recordings, schedule, and everything. Yeah. Okay, there's the link. Okay, so let me go in order of questions. Someone at like the very beginning asked fundamental theorem of calculus part 2. Wait, are they still here? Hopefully. How to use that. Okay, that was used in this question. So this is from fall 2012, number 3. When it's asking you to compare the values, but let's focus on this m. So m is this limit from this to this. But how do you even find the integral of e to the negative t squared dt? Like if you use substitution, your derivative would have a t term in it, but we don't have any other t's in here. So how do we take this integral? Well, so this is why this was multiple choice, because you are not expected to know how to do this integral, but you can think this limit as x goes to 0. What's the first thing you think of when you see a limit? You plug in what your x is going to. So if you imagine plugging in x equals 0, in the denominator, you get 0. That's already a caution sign. Like you got 0 in the denominator. So let's assume maybe this top thing will also give you 0. Because if so, then plugging it in would give you 0 over 0. That's an indeterminate form. So you have to use L'Hopital's rule. L'Hopital's rule says you can take the derivative of the top and the derivative of the bottom. What is the derivative of the top? Derivative of this, derivative of this integral, so the numerator. How do you do that? That's by the fundamental theorem of calculus part 2. The derivative of an integral says it's exactly the same thing inside here. You just plug in this other bound. So this upper bound is x. So you just replace the t's with an x. So the derivative of the integral is e to the negative x squared. So you get e to the negative x squared. What's the derivative of the denominator? That's 1. And now when you plug in x equals 0, what is e to the 0? Anything to the 0 power is 1. So you get 1 over 1, which is 1. So this limit equals 1. And we had to have known this rule in order to do that. Yeah, question?
Are you gonna post this also to your like website? Because I
Yeah,
know
I'll
that's
post-
like a
yeah.
different thing.
Yeah, I'll post this also. This will be under nice final exam problems that I found. Okay, so yeah, go ahead.
Also, how do you know to assume that the numerator is also 0?
Because how else do you want to how do you compute this integral? Like you can, the techniques we've learned are u sub. You can try u sub. U is negative t squared. Then du is negative 2t dt. Before I said we're not allowed to divide by variables. So there's no other way to use u substitution for this. Other technique, integration by parts. But what are you gonna, if you choose, okay, u equals negative t squared, du equals negative 2t e to negative t squared. But remember in the formula for integration by parts, you're going to be taking integral of v du. So this du is going to end up here again. How do you take the integral of that? Like, so right now, because we don't actually have to find what are these actual numbers, like you can approximate. Like that's why it says like which is less than this and this. Yeah, and the same trick with n. Like how do you find this limit? What you are going to end up doing is trying. So this is the limit as x approaches 1 from the right. So from the right, maybe a very, very close point to 1, like 1.1. You try it out and you get 11. So now that you know approximately what these limits are, you can figure out that the answer will be f. Now, maybe also note if they had said e to 2t on the other hand, e. Yeah, on the other hand, we know what that is. That is 1/2 e to 2t. So this we can compute, but because this is t squared, that makes it difficult to compute. Okay, any other questions on this one? Okay, let me look at, wait, are they still? Okay, maybe they're not here anymore. Spring 2013 person. Okay, then I'll go to the question on prep quiz. We go over question 2 from the prep quiz on Taylor series. Yeah. Okay, so let's see. Prep quiz on Taylor series. Guess that's 15. Oh, this was not okay. Okay, is this person also here? Okay. So let's do this example. So compute the degree 5 Maclaurin series for natural log 1 plus x squared. Okay, so we need to know what even are the Maclaurin series. So I have here, I know the Taylor Maclaurin series for natural log 1 plus x squared. I know the Maclaurin series for e to the x. Okay, and from that, I can do some manipulation. So in the red are facts we know. before we even multiply anything out, first we need to know what is the Taylor polynomial for, or the Maclaurin series for 1 plus x squared. So we know what it is for x. The only difference now is we have x squared. That means that wherever we see an x, we're going to replace it with x squared instead. So that gives x squared minus, oh, I see an x there, so x squared 2 plus, oh, I see another x, so x squared cubed over 3 factorial. Oh, wait, just 3, no factorials. Okay, so what does that give us? X squared minus x to the 4th over 4 plus x to the 6th over 3. Okay. What about e to the 6x? So wherever we see an x, let's do 6x. So I see an x there, 6x. I see another x there. And be careful about parentheses here. They are important. Plus 6x to the 4th over 4 factorial, etc. So now we have to multiply them. So natural log 1 plus x squared e to 6x will be, we're going to be multiplying this first natural log one. Also put the dots just so people know. And you should also put the dots in your, if this showed up. Plus, okay, maybe I will not factor this. I will keep it as 6x squared. Wait, I'll keep it as 6 squared x squared. 6 cubed x cubed. X to the 4th over. Oh, sorry, I wrote. Thank you for catching that. So it's over 2. And Okay, everyone following along so far. Okay, and now what does the question say? We only need up to degree 5. So let's start FOILing. And each time we get above a degree 5 term, we can stop that process and move on to the next term. So I'm going to start in green. We get x squared plus 6x cubed plus 6 squared x to the 4th over 2 plus 6x cubed x to the 5th over 3. And we know that this next term, so I didn't write it out, but it would have an x to the 5. And x to the 5 times x squared would give you a 7th degree term. And we're only stopping at 5. So you don't need to continue the green FOILing. What about, so let's move on to the next term. In the orange, we have minus x to the 4th over 2. Then we have minus 6x to the 5th over 2. Okay, going one more would give us an x to the 6th term. We don't need that. So stop with the orange. Now let's do blue. Over here we have plus x to the 6 over 3. Oh, we're already going over because we wanted to stop at 5, right? So we don't even need to continue the blue thing. And continuing multiplying the blue thing would keep giving us terms higher. And even here, if we started another sequence, it would give us even higher terms. So stop there because that's the degree 5 polynomial. So this is the answer. Okay, any questions on that? Yeah, of course. Any other final questions, clarifications?
We have a question.
Yeah.
This is from prep quiz 15 question 2, right?
Yes.
And it says to add the coefficients of that. How would you do that?
So coefficients of x to the 4th. So where are your coefficients of, so x to, so x to the 4th, we see here, x to the 5th, x to the 4th, x to the 5th. So what are the coefficients in front of those? Well, we have a 6 squared over 2 term. We have a 6 cubed over 3 term. We have a 1 over 2 term and a 6 minus 2. So whatever this number is your answer. Okay, any other questions? Yeah, I would. Yeah, I mean, it's always good to, okay, the question was, should we try to do spring 2018 test before tomorrow's review? So whenever you do practice exams, especially for the fall 2021, if you haven't done it, I would recommend doing it on a timer. Like time yourself to however long this exam is, 100 minutes, and try to do it and see what you get. Even if you get some of the questions correct, tomorrow when I go over it and you see the solutions, you should make sure you understand all the solutions. Maybe the next day, take the test again to make sure you really remembered it. Don't just like look at the solution and be like, oh, I got it. Nice. Because maybe you somehow got it that time but there's like some small thing that you forgot about. And for the spring 2018 one, yeah, I would also recommend doing it before we do it. Go over it tomorrow. Oh, the exam on Rimmer thing, it says 100 minutes, but yeah. Should I do it with open cheat sheet or like open notes? Maybe if your cheat sheet only has like important formulas, like the trig identities that might be hard to remember, maybe do it with the cheat sheet. I think a good technique that I've had with preparing for finals is trying to do it without a cheat sheet. Because with a cheat sheet, that takes away time, right? You have to look at your cheat sheet and see, oh, where was that formula, etc. And it uses up minutes that you could be using thinking about your question instead. And also, like if you know things more by heart, you'll also be able to look at the question faster and not be distracted by, oh, I have to find the formula or find what I wrote on this cheat sheet, right? So it's always good to know all the material by heart. Yeah, of course. Any other last minute questions? And all of this will be posted on my website. I'll post the recording as soon as it's uploaded to the cloud. All right, if not, then I will end recording.